All right, so this begins our usual schedule of classes this week. We're through those first 2 weeks. Of course, we meet today and tomorrow because we had no school yesterday. So your A-day classes will meet on Wednesday this week, but Thursday and Friday are not mandatory unless your grade's below 70%. So for those you have everything turned in and have scored over 70%, then you're going to be great for Thursday. Won't need to come to this class. If there's anyone who, oh, let me look. Just look to see if there's anyone who is under 70% in this class. I'm not sure there is. No, everyone in this class is over. So nobody has to come Thursday. Now, be aware, I will be in class Thursday morning. If you need help with something, if you're working on this week's and struggling, you can always come to class. Thursdays, I only have class till like 8:15 because we have a teacher's meeting during the last part of this hour on Thursdays. But Thursday, I will be here, and none of you are required because everyone's grade is well above 70%. So good job. Keep it up. Make life easier on yourself, and have some extra time free from class. So, all right, since we got everybody here, well, almost everybody here, we got a bunch of us here. Not everybody. We got two people that are sleeping in this morning, but hopefully that's a short-lived thing. Too much partying yesterday, I guess. Too much going on, so people couldn't make it to school today. We had the presidential inauguration yesterday. We had Martin Luther King Jr. Day, and we had the football national championship for college football. So there was a lot going on yesterday, and kind of maybe people partying too much. I don't know. But let's take a look at what's up on this week. Put the screen up. Okay, Algebra 3. Let's go to our grade screen. Okay, this week, January 26th is this Sunday. So we have geometric sequences. Geometric sequences. And then next week we'll do the geometric series. Very similar to arithmetic, just not. Right? So let's go switch to look at 5.03. In the following activity, you'll be shown some sequences. So here we go again. We got to guess the next numbers. I've got the chat open where I can see the chat. So open your chat. Your objective will be to identify the pattern within each sequence and use that pattern to give the next three numbers. So let me see if I can make this a little bigger. Be able to see it really well. Find the next three terms in this sequence. And our sequence starts with a 1, then there's a 4, then there's a 16. Quite obviously not arithmetic because it adds 3 and then it adds 12. So that is not arithmetic. Something else is going on this morning. So put it in the chat what the next three numbers are. Lilith has got that calculator going this morning. You may need a calculator for some of this. So I'm seeing answers there. Let's see if I don't want to cheat you if you're working on that. If you need to use your phone as a calculator. We do have two different answers on the screen right now. So just letting people know. So your next person could break the tie here. Got one of each. So, of course, the first thing you have to do is identify what's going on, right? Because it's not adding each time. Lilith says, oh, wait, I goofed. I hit an extra multiplication there. Kai is going to break the tie. Yeah, Lilith had the number. She just did also like another number there too many times. It's multiplying by 4, right? 1, 4, 16, 64. 64 times 4, 256, and that times 4 is 1024. So we submit that. That is great. That's it. We got 4 of these. So here's the next one. 2, -6, +18. Oh my goodness. What's going on with that? This is a sequence of numbers. It is. It is. This is a geometric sequence. So Lexus is on top of it. And you got to figure out what it's multiplying by, which you can always go backwards and divide. Divide by the number in front of it. Like -6 divided by 2 or 18 divided by -6. You can work backwards to figure out what is the pattern. Just like on arithmetic, we can subtract to see how much was added each time. This one we can divide. Divide 16 by 18 by -6. So what is happening? It is multiplying by -3, right? 2 times -3 is -6. -6 times -3 is 18. 18 by -3 is -54. If you multiply that by -3, it goes back to a positive 162. And then finally to a -486. Submit. Excellent. Yes, it is multiplying by -3 each time. Let's look at the next pattern. I don't know why it has all these dollar signs on here. It just needs one at the beginning. $1, half a dollar, a quarter of a dollar. All those dollar signs are kind of confusing. Oh, Alexis caught on in a hurry there. 1, 1/2, 1/4. And we're not supposed to convert to a decimal this time. We're supposed to use the slash, the division symbol. So yeah, so you can see what's happening. The denominator is doubling each time. 1/1. We don't write 1/1. We just write 1. 1/2, 1/4, 1/8, 1/16, 1/32. Yeah, the denominator is doubling each time. So it's actually being multiplied by 1/2, by 1/2. Hey, we didn't put all those dollar signs because I don't know what they're there for, but yeah. All right, here's our last one. Oh, you knew they had to do something with the decimal, didn't you? 6, -1.2.24. This time we're supposed to enter as a decimal. What is going on? 6, -1.2, positive 0.24. All right, I got a couple of answers in the chat. Yeah, well, let's see. So the next one would be a negative because we have a positive and negative. Negative 0.048. Let's see. Then the next one, it's alternating because it's multiplying by a negative each time. So the next one goes back to a positive. Well, I wonder if it wants the 0 in front. I wonder if it matters because it put a 0 in front. If I don't put it in there, it might count it wrong because it's just a computer. And then we got negative 0.00192. So right, there should be another 0 in there. Wait a minute. So what they're doing each time, it's really kind of dividing by 5 or multiplying by 1/5. So 0.0, let's see. Put the calculator up here. I have a negative 0.15, 0.009. Dividing by -5 or times negative 1/5. Let's divide by -5. I got 1/8. Why did I get 1/8? Is that right? 6 times. Let's do it as a parentheses 1/5 negative 1.2. Okay, so negative 1.5. So 0.24 times parentheses 1/5 as a negative. Is the 048 times parentheses 1/5 as a negative. There's our 0096 times 1/5 as a negative. Okay, there it is. 000. Just two zeros, 192. And that's right. Didn't have to doubt you at all. Very good. Okay, let's shrink this back down. So notice that each of the terms within the sequence was separated by a common multiplier or ratio. The first list we had 1, 4, 16. They're all separated by a common ratio of 4. It's being multiplied by 4 each time. So this is a geometric sequence. The arithmetic sequence we were adding each time. This time we're multiplying each time. Sometimes by a fraction, sometimes by a negative number. So how can the expression or process be determined for a geometric sequence? So we're going to have some more formulas. So have your pencil and paper ready to write down some more formulas. What functions combine to create an explicit formula? So we're going to have a recursive and an explicit, just like we did for arithmetic. And what possible restrictions exist on the domains and ranges? All right, let's go to page 2. A geometric sequence is a list of numbers called terms, just like we call it arithmetic, which share a common ratio. See, last time they had a common difference. This is a common ratio. In this following activity, you'll look at more sequences. Some of them are geometric, while others are geometric or arithmetic. So our job is to separate them. All right, so we got another one of these. I'll still use the chat. Is this geometric or not? Just put yes or no. Yes, it's geometric. No, it's not geometric. 4, 12, 20, 28. Alexa says no. Lila says that this is non. Bella, no. Kai, no. So nobody believes this is geometric, huh? Well, at least 4 people don't. So the rest of y'all are still half asleep. Thank you, Madison. No. Oh, you're correct. It is not. How about this one? 5, negative 15, negative 90, 270. Yes or no? Right away, we see it's not arithmetic this time, right? But does that mean it's geometric? Well, people are saying no. They're saying no. That's it. I mean, it's not arithmetic, but it's not geometric either. Now we got a positive and then 2 negatives in a row and then a positive. That right there tells you this cannot be geometric, regardless of what it's multiplying by. But let's see. It multiplies by negative 3, and then it multiplies by a positive 6, and then a negative 3 again. So that's not consistent. That's not going to work. Oh, well, this is interesting. 1, 1, 2, 6. No, it's like, wait. It goes from 1 to 1. It multiplied by 1, or it added 0, or it. Yeah, I don't know anything we can multiply with to come up with this. That's just nothing there. So how about this? 7, negative 70, 700, negative 7,000. Yes, I see lots of yeses coming up there. Believe it is a geometric sequence. Well, let's see. If it is, it should be having a common ratio each time. The common ratio is 7 times negative 10 would be negative 70, and negative 70 times negative 10 would make a positive 7. Yeah, that looks like that's going to work. How about this? 9, 45, 225, 1,125. Let's see. 45 divided by 9 is 5. So we know it multiplies by 5 with the first 2 terms. Is 5 times 45, 225? Yes, it is. 225 times 5, 1125. Yeah, it is. This is multiplying by 5 every time. So there we go. See, they're reviewing all of them in case you missed any of them. 1, 1, 2, 6. Well, there's a pattern between the terms in this sequence. It's not geometric since the ratio between each term is not consistent. So it's, yeah, times 1, then times 2, then times 3. So there's a pattern in that one, but it's nothing that we're working with. Common ratio of 5. We got that correct. This is times -3, then a +6, then a -3. So that'd probably be times a +6 next time, but that's not consistent. -10, and then we had that first one. So great job. Not going to fool you this morning. You're wide awake, ready for this. And of course, just like arithmetic, we may see it in different forms. We may have a list like this, 1, 3, 9, 27. We could have a table. The first term is 1. The second term is 3. The third term is 9. The fourth term is 27, which if we graph this table, we'd have the first term, the second term, the third term, the fourth term, and we can see the graph is much different than arithmetic. Arithmetic makes a nice linear graph. This is not. You'll notice on the graph, there's not a continuous curve. We didn't connect those points. We cannot connect those points because then that means we're including numbers in between there as part of the sequence, and they are not part of the sequence. This is a discrete set of points. A set of data is discrete if it's finite or if there are spaces between the numbers on the number line. Like the number of students in a class is a discrete set of data because only whole numbers are used. So the sequence only exists at those points, but not between there. So it looks like an exponential function, but an exponential function is continuous, where we would have all that connected with a line, but we don't connect it when it's just points in the sequence. All right, there are 2 methods of determining the terms of a sequence, just like last time. So here's our recursive. Let's see, I'm going to write this down and then we'll play with it. Okay, it says, assume that we have this sequence. Oh, that's not focusing well at all, is it? The first term is 3, and then this is our formula that we can use. So if we want to find the second term, a sub 2, we take 4 times a sub n minus 1. That, if this is the second term, that'd be the first term. So it equals 12. So our sequence is going 3, 12. If we want to know the third term, we take 4 times the second term. A sub n minus 1 would be the second term. The second term was 12. So our term is turning into that. Let's see. I need some extra light, but not that close, apparently. Yeah, 3, 12, 48. So you can see what our sequence is doing there. It's multiplying by 4 each time. And starting with our first term, we can find each term. So with our geometric, this is a geometric sequence. And this is the recursive form, which recursive means you need to know the term before it. A sub n equals the common ratio times a sub n minus 1. Our common ratio. And of course, you need to know what a sub 1 is, because it has to tell you what the first term. So a sub n equals r times a sub n minus 1, with r being the common ratio. So there's our first new formula for the week for geometric sequences. Have that down in your notes. Let's go back and let's look at the explicit. So an explicit formula allows you to calculate any term directly, unlike the recursive process where you have to know the one before it. An explicit formula is useful in ways the recursive process be boring, like if you were to find the 27th term of a geometric sequence that goes 8, 4, 2, you'd have to list every term till you get to the 27th. Yeah, but who's got time for that? So we're going to get to the explicit formula coming up here. Deriving the explicit formula. So at this point, you should understand how to identify geometric sequence, which you guys did great at identifying what is a geometric sequence. And we can find the next term, because you guys found the next three terms. But what if you're asked to find the 11th term of a sequence like 2, -6, 18, -54? You'd have to list, do a little math to get to the 11th term. But let's see if we can find a formula here. So let's look at these clues. First term is 2. So we saw that in the sequence right there. 2 is the first term. And then the second term is we multiply that by -3, because we know that 2 times -3 is -6. Then, to find the next term, we can start with that 2 again, multiply it by -3, and multiply it by -3 again. If we multiply it by -3 twice, we'll get the 18. And to find the fourth term, we can start with that 2, multiply it by -3, multiply it by -3, multiply it by -3, and we'll get to that -54 as the fourth term. That's a good hint right there. So where does the 2 come from? The 2 is the first term, right? Check the answer. Yep, that's the first term. What's the -3? -3 is our common ratio. We can figure that out just by dividing backwards. -6 divided by 2, or 18 divided by -6, or -54 divided by 18. So the -3 is the common ratio. What is the fifth term? The exponent, how's the exponent on the -3 determined? The exponent is how many times we've multiplied by -3. Start with the first term, 1, 2, 3, well, the fourth term. So that's one less than the term we're looking for. The exponent on the -3 comes from the position of the term in the sequence -1. So what is the fifth term? Well, the fifth term would be -3 to the fourth power times 2. So -3 taken to the fourth power times 2. So it should be 162. There it is, 162. All right, we're going to see if we can derive a formula by taking this fifth term and working backwards. So we're going to get our formula for our notes right here. So let me get this plain.
The fifth term of the geometric sequence is 162. 162 can be written as 2 times 81. 2 represents the first term in the sequence, which is indicated as a sub 1. 81 is the result of 162 divided by 2. 81 can be written as -3 to the fourth power, where -3 represents the common ratio between each term of the sequence. 4 is the result of the exponential equation 81 equals -3 to the power of x. Use the variable r to indicate the common ratio. 4 is the same as 5 minus 1. 5 represents the fifth term in the sequence, and 1 is the difference between 5 and 4. The variable n is used to represent the position of the term in the sequence.
So that gave us a formula. I don't know if you caught it right there at the end. A sub n equals the first term times the common ratio raised to the power of n minus 1. Raised to the power of n minus 1. So we're going to play with that some here. Here it is. A sub n equals a to the first here. I'm going to put it on I've got it on my paper, actually. I'm just going to put it up on your screen. So there's our two formulas that we should have that we're going to use this week. Should have it in your notes. So the recursive formula for a geometric sequence, A sub n equals the common ratio times the term before, a sub n minus 1, common ratio. Explicit formula, A sub n equals the first term times the common ratio raised to the power of n minus 1. So if we're finding the 20th term, we're going to put a 19 up here. So the common ratio taken to the 19th power. So a sub 1 is our first term. So I'll leave it up there for just a moment. Make sure everyone's got a chance to get that in our notes. It's also in our lesson, but so what do the variables mean? We notice that a sub n. Let's see, a sub n is the term we're looking for. That's the desired term of the sequence. A sub 1 is the first term. R is the common ratio, and n is whichever position term. So n minus 1 would be one less. So looking back at that sequence, they had 2, -6, +18, -54. Finding the 11th term, we just have to substitute the numbers in. So let's do that in our paper just to have a nice example written down. Here's the sequence they were playing with. -54. 2, -6. So we know the common ratio is -3. Because if we divide backwards, -6 divided by 2 is -3. 18 divided by -6 is -3. And we know that a sub 1 is right here, is 2. And that's all we need for this formula to find the 11th term. So the 11th term uses the first term times the common ratio raised to the n minus 1. N is 11, so this is to the 10th power. And we just simply put it in our calculator at this point. 2 times -3 raised to the power of 10. So we expect our 11th term to be 118,098. Gets big in a hurry. 118,098. Let's see. And that's exactly what they get as well. Yeah, -3 to the 10th power, which they went in and simplified that as 59,049, multiplied it by 2. You may be thinking the geometric sequence formula looks remarkably like an exponential function, where the variable is in the exponent, and you would be correct. Geometric sequences, geometric series are used for events that are more static in nature, where exponential functions support continuous events. Like interest rates that are applied once a year to a savings account would be better as a geometric series, but accounts that earn interest continuously would be better as an exponential because it counts all those little numbers in between. All right, so here's a summary of the two formulas side by side. We have them on our paper, one above the other. But if you didn't get that, or if you couldn't read my writing, I'm trying to do good today. I think I'm doing all right on writing today. There they are in your notes at the bottom of page 3. Bottom of page 3 in our lesson. Okay, so page 4. So one way to think of the explicit formula is a combination of functions or two separate parts. You've got the a sub 1, which is just a constant. It's just a number. And then you have the r in minus 1. So a sub 1 is a constant. This is an exponential expression because the variable is in the exponent, r raised to the n minus 1 power. And when we multiply those together, that's what gives us our explicit formula for geometric sequences. And the domain and range. So if we keep an eye on that, what are the possible x's? What are the possible y's? All right, so the domain, the domain for geometric sequences is restricted to all integers greater than or equal to 1. Think of the table we saw. Let's go back to the table. That helps us easily picture how the domain works. There it is. The domain would be the ends. And that's the number you put in. This is the number you get when you put the n into the formula. And if you look at it, 1, 2, 3, 4, this is which term it is. The first term, the second term, the third term, the fourth term. So if we understand that, it's easy to figure out that the domain of a geometric sequence, a series, like a sequence is right. Yeah, geometric sequence. The domain would be whole numbers that are greater than or equal to 1. Because it's the first term, the second term, the third term. It's not the 2.5 term. It's not the negative third term. It's not the 0th term. It's only numbers, whole numbers, 1 or larger. And as we saw with the list of terms, the 1, 3, 9, 27, that could be anything. It could be negative numbers. It could be decimal numbers, fractions, whole numbers. So there's no restriction on that. So let's put that in our notes because these assignments always ask about that. The domain of geometric sequences in general. Integers greater than 0. That's basically it, right? Only integers, only whole numbers. And it can't be 0, but it can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the domain. The range, that's not a good E. All real numbers. Now, this is in general. Now, for a specific sequence like this is the range, 2, -6, 18, -54, and listing all the terms. That is the range. List the numbers in sequence. It's not everything from 2 to -54 because that would include 3 and 4 and 1 and 0 and -1, all those things. You just list the numbers in the sequence. That is the range. But the domain would be the first term, the second term, the third term, the fourth term. So it's all integers greater than or equal to 0. So you can add that to your notes because it generally is going to ask you something about the domain. When we do our assignment, it generally asks something about what is the domain of this geometric sequence? And you go, oh, it's all the x's greater than 0. But it has to be integers. We'll highlight integers on that. Page 4. Let's talk about the domain and the range combination functions. So the domain for geometric sequence is restricted to all integers greater than or equal to 1. Right? So 1, 2, 3, 4, 5. The domain is the term number. So there's no terms between the first and second term. So that's why we don't have 1.25 or 3 halves or anything like that in the domain that does not meet the restrictions. And there's no negative terms. In a race, there isn't a second place, first place, negative first place. There's only a first place, second place. We don't have a negative first place. So the domain of sequences is all integers greater than or equal to 1, or all integers greater than 0. The range can be any number, positive, negative, whole, rational, doesn't have the same restrictions. You can have a tree that's 43 feet tall and one that's 43.2 feet tall. All numbers are welcome. So in general, it could be any range, but if you have a specific sequence you're looking at, the range is the numbers that are listed in that sequence. All right, let's do some examples. And this is our lesson summary. So let's do these 2 examples. Write this down. 14th term. First one's 6. The 8th term is this big, nasty number right here. So we don't have the 7th term, so we're not talking about the first sequence. Let's plug what we know into this and see if we can work backwards. A sub 8. So A sub 8 is -468,750. And that equals the first term times R to the 7th term. Right? Because it's n minus 1. So we need to solve for R. Divide both by 6. That's our first step. So let's get a calculator out for that. Not going to do that in my head this morning. Where's the calculator? There it is. All right. 468,750 negative All right, there it is, negative 468,750 divided by 6. So this is negative 78,125 equals r to the 7th power. Now we need to take the 7th root of both sides. So it will just equal r on this side, but the 7th root, well, let's see. Will my calculator do 7th root? It will. Y root of the x. So we can just type in, oh, I've already got typed in. So let's take that. And it wants to know what root I want. I want the 7th root of that number, which is negative 5. So our r is negative 5. Okay, good. That helps knowing what our common root is. So now that we know the r is negative 5, it wanted us to find the 14th term. So a sub 14 equals first term, common ratio, and n minus 1, so to the 13th power. So the 14th term will equal, let's see, 6 times negative 5 raised to the power of 13. Wow. So this is negative 7,324,218,750. There's the 14th term in that sequence. I'm glad we weren't trying to do it with this formula where you got to figure out the 13th and the 12th and the 11th and all of that, because that would have taken some time and some big numbers. Negative 7 billion. Let's see what it says. First, you got to find r by substituting what we know in there, taking the 7th root, find it to be negative 5. That's exactly what we did. And then we substitute back in to find negative 7 billion, 324, 218, 750. All right. Fun stuff there. Example 2. So a real estate developer is clearing 450 acres of land to build a commercial development. Every day, half of the land is cleared, which means your workers are getting lazier and lazier, because the first day they cleared 225 acres, and then they only cleared half of that the next day and half of that the next day. How many acres are left after 10 days? Hey, if they can clear half of it in the first day, they should have had the second half done the second day. I'm going to fire them and get somebody else. I'm just giving a hard time. Round the solution to the nearest hundredth. So type your answer to each question in space provided. Enter a fraction by entering the numerator, a slash, and then the denominator. So what is the first term of the sequence? Well, we started with 450 acres. So that's our first term in the sequence. All right, the next question. What is the common ratio? Well, it says every day, half of the existing land is cleared. Every day is half, so that should be 1/2 as our common ratio, because that says every day, half. We've got it. R equals 1/2. So next question. Type your answer. What is the value of the variable n? Well, it said how many acres are left after 10 days. So we expect that to be 10. And then finally, now you can apply the geometric sequence formula. How many acres are left after 10 days? Round to the nearest hundredth. So we're going to put it as a decimal. And use a 0 before the decimal. Okay, so they want 0 point whatever. So let's write this down. 450 is our a sub 1. R equals 1/2. And 10 days is our n. Okay, I'll switch that over. 450 acres, R is 1/2. 10 days is our n. So we're using our explicit formula. a sub 10 equals first term 450. The ratio is 1/2, or you can do 0.5. That's the exact same number, right? Because this is a terminating decimal. And n minus 1, 9 times. Calculator. 450 times 0.5 to the 9th power. So there are 0.87890, etc. And they want us to round this in our answer to the nearest hundredth. So that's 2 decimals. So 0.88 then. 0.88. Submit. That's it. Yeah, we just take that 1/2 to the 9th power, which apparently is 0.001953225 times 450. So less than an acre left after 10 days. Okay, here's another example. If you'd like to go through one, we're going to do a practice problem or two in the next page, but here's another one you can put in your notes if you need another example. Find the 9th term of this sequence. So we can use that explicit formula. N will be 9. The common ratio you can tell is 7, because -3 times 7 is -21. -21 times 7 is -147. Substitute it all in, get your answer. Lesson summary. There's those questions we had at the beginning. So a geometric sequence is a list of numbers where the ratio is consistent, not the difference. A specified term can be found using this, which is the explicit formula. They give it to you again down here. So they list it here and then they repeat it because they give you the recursive formula and the explicit formula. And the domain is all integers greater than or equal to 1. There's no restriction on the range. All real numbers are possible. And it's a combination of a constant function and an exponential function to give us our geometric sequences formula. All right, we got a page of practice problems. Let's take a look at that before we look at our assignment for the week. Find the indicated term of the given geometric sequence. There's five practice problems there. Okay. I'm going to let you guys work this as well. I'm going to work it, but I'm not going to show you until you get your answer up on the screen. So put your answer in the chat. The 10th term, I'll go ahead and make this a little bigger just so you can, I mean, you have it in your lesson, but you probably don't have it open. Find the indicated term. Find the 10th term of this sequence, 2, 8, 32. And it's one of these. It's probably not 38. We can probably rule that one out right now. All right, work on that. I'm going to work it on my paper, and then we'll come together and see if we get the same answer. My calculator, but I'll move to another page. We can't see my calculations. If you don't get one of the answers that's on the screen, that means there's a problem, right? Because you should have one of these 4 answers. All right, I see some answers populating our chat here. All right, here's how I did it. 10th term, A1 is 2. Common ratio is 4, but it's 2 times 4 is 8. 8 times 4 is 32. So A sub 10, just substitute it in using this formula. A sub n equals the first term times the common ratio raised to the power of n minus 1. Calculator work, 524288. Great job. That's what everybody else was getting there too. I'm glad I got the same answer you did. 524288. Great job. And it shows you how to do it there as well. Let's look at our second one. Find the seventh term of this geometric sequence. All right, let's try that one. Seventh term. And it gives you the sequence 5. Good morning, Mr. Granderson. -10, +20. So see if you can figure out your common ratio. Hopefully you'll get one of those answers on the screen. I'll bet it's not -7. They always give us a throw out answer there. Yeah, I'm sure it's not -7. That's got to be wrong, right? That would be between the first and second term. I'm seeing some answers pop up. Well, let's just beat Alexis on this one. Last time it was the other way around. Guy's going with -1,000,000. Well, let's put it up on the screen and see how this works out then. Let's see. The terms, it had 5, -10, +20. So when we went backwards, we found out it was multiplying by -2 each time. So that was our common ratio. R equals -2. Our first term was 5. We went to 7th. So it's 5 times -2 to the 6th. 1 less than the 7. -2 to the 6th is 64. -2 times -2 times -2 times -2. You have to do that in your calculator. And then times 5 is 320 was our answer. Let's see if it tells us we're right. 320. Yes. So the common ratio was -2. All right, we'll try one more while we're here. So. Oh, yeah, this is a good one for us to try because it doesn't give us the common ratio. It gives us the first term is -4. The sixth term is -972. And we need to find the 11th. All right, this is a good one for us to practice together. Find the 11th term where it gives you the first term and the sixth term. And it's one of these -200,000 terms. All right. This will be a good one. So try this. I'll work it on my paper. We'll come back together. All right, Alexis is quick. She got an answer quicker than I did. We'll see if it's the same answer. It is one of the 4 on the screen. That's a good sign. Oh, see, Alexis, she's already done through this. So this is old hat to her. She's already practiced. That makes sense. Yeah, Alexis went through this lesson and already solved all of these ahead of time. So she's already practiced on these. So she's on top of it. That's great. Anybody else got an answer on this one? It's one of those where they don't give you the common ratio, so you got to use the formula and work backwards to find the common ratio. I'll show you how I did that in just a moment. Give me a chance to see if anyone else gets an answer. All right, if you're still working on this, that's good. I'll go ahead and put my work up on the screen. See if you're going down the right path. Our first term was -4. Our sixth term was -972, and we're trying to find the 11th term. So we had to go to our formula, this one right here, the A sub n, A1, R n minus 1. Substitute what we know. We know the sixth term is -972, so I substitute that in. I know the first term is -4. I don't know the common ratio, but I know this one right here. This would be to the 5th power because this is the 6th term. This is n is the 6. So when I get this formula set up, I can divide by 4. negative 4, divide by negative 4, and that equals 243. 243 equals r to the fifth. So now I take the fifth root. The fifth root of r to the fifth is r. The fifth root of 243 is 3. It's 3 times itself 5 times. 3 times 3 times 3 times 3 times 3 is 243. Now that I have the common ratio, same formula. The 11th term would be the first term times the common ratio times 10, 1 less than the 11. 3 to the 10th is 59049, 59,000. Take that times negative 4, the negative 236,196. So I got the same thing that Alexis got there. Negative 236,196. We'll put that in here. And there it shows you all the work on the screen, down to getting the 243 equals r to the fifth. And you have to take the fifth root of both of those sides to get the common ratio. So that's a little trickier than the others, just because you have to take the funky root, in this case, the fifth root of a number. And then you have 2 more problems you can look at there. Sixth term gives you the first and third. First and third. And then there's another one. Let's look at the assignment. Find the first problem right off. Find the 12th term where they give you the first and the sixth. So the very first one is just like the last one we worked, where you have to find the common ratio before you can find the 12th term. Got to work backwards. This one gives you the first and the fifth, and you have to find the 17th. And you'll notice there's decimals involved, so round it to 2 decimals. The nearest 100, they got 2 decimals right there. So again, you got to work backwards to find the common ratio, and it's going to be a decimal. Let's see. A bacteria culture begins with 13 bacteria, which triple every hour. How many bacteria are grown during the 10th hour? Okay, there's your A sub 1. Here's your common ratio, triples. And then the 10th hour, that's the N. N equals 10. R equals 3, A1. So you just plug those numbers in. Given the functions f of n equals 500 and g of n is 9/10 to the n minus 1, combine them. So how do you combine them? Do you subtract them? Do you add them? Do you multiply them? Or do you multiply the 500 times the 9/10 first and then raise it to n minus 1? So spoiler alert. These are multiplied, right? It's 500 times the ratio, 500 times the ratio. So we know that's right already. Given the sequence below, create the explicit formula and list any restrictions. So if our first term is 3, where does that go? It's one of these two, right? Because the first thing after the equal sign is the first term. First term is 3. And then what's the common ratio? Is it -2 or -3? First term is 3. Next term is -6. So yeah, we know that one already too. 3 times -2. And the n is greater than or equal to 1. So there it is. Let's look at the calculator for this just real quick. There is a calculator built in the Buzz. If you haven't used that, let's see. Will it do? Yes, you can do like the fifth root of a number. Let's go to that last one, 243. And if you click this Y right here at the bottom, Y roots of X. Oh, you got to do it the other way around. Look, I'm taking the 243rd root. So that's why I look at these calculators and see what does it want first. If I want the fifth root, I take 5 root, and now it shows this is the fifth root, 243. Well, see, that looks kind of like we need it to look. The fifth root of 243 is 3. So on this calculator in Buzz, you type the root first. If I want the 11th root of a number, what one did we do earlier? We did the 7th root of a number earlier. So if I want the 7th root of what? It was -78,125. There. The 7th root of -78,125 was -5. That's the one we did earlier. So you can use this little y roots of x button right down here in the bottom row to find like the 5th root, 7th root, 11th root, whatever root you need. It's right there. So I just wanted to show you that it's in the calculator in Buzz, right up here in the menu, calculator. So it is available for you right there. Okay, guys. Everyone's doing super. You got everything turned in. You got another 25 minutes in this class. If you want to do these 5 problems quickly, you can be done for the week 2 days before your next class hits. So I'll give you the rest of this time for your work. I'll be here if you need help, but you guys are done for the week once you get this turned in. So have a great week, everyone. Nobody's required to be your Thursday. I'll be your Thursday. You're not required. So if I don't see you again this week, I'll see you next Tuesday. So great job, Algebra 3 folks.